Before we start our presentation, I would like to share a video about conductivity atomic force microscope.
Conductive AFM. The conductivity of the sample can be measured by performing a contact AFM scan with a conductive biased tip. Regions of high conductivity on the sample surface allow current to pass through easily, while regions of low conductivity will have a higher resistance. Conductive AFM yields both the topography and the electrical properties of a sample surface.
Assalamualaikum and good morning. Today we will be presenting about Conductive Atomic Force Microscope CAFM. This slide will be presented by me, Siti Zaharah binti Jamaluddin, and also Nurul Damia binti Roswadi. In this presentation, we will cover introduction of CAFM, basic component, basic working principle, methodology, interpretation of result and data, conclusion, and also application of CAFM. I will start with introduction of Conductive Atomic Force Microscope. CAFM is a mode in atomic force microscopy (AFM) that simultaneously measures the topography of a material and the electric current flow at the contact point of the tip with the surface of the sample. The topography is measured by detecting the deflection of the cantilever using optical system which are laser and photodiode, while the current is detected using current to voltage preamplifier. CAFM is a common technique to study electrical properties of a wide range of materials, including nanoparticles, nanowires, carbon nanotube, 2D materials, thin film coating, and bulk material. It can be used to study leakage current, semiconductor device failure analysis, including diode on-off switches. We move to the next slide, basic component of CAFM. CAFM consists of cantilever and tip, laser, a scanner that controls the XYZ position, detector and the feedback control, and also image and current display system. We move to the basic working principle of CAFM. There are three important elements. First, the probe tip must be conductive. Second, the voltage source is needed to apply a potential difference between the tip and the sample holder. Third is a preamplifier is needed to transform the analogical current signal into digital voltage signal so that can be read by computer. Then a sharp conductive tip is in contact mode with the sample. The sample is frequently attached to the sample holder with conductive tip or paste. The tip pressure on the sample is controlled by the user and monitored via cantilever deflection. As the tip has only local contact with the sample, the measured resistance is influenced by the sample's local resistance. The tip usually placed in a direct contact with the sample surface before being scanned over it with a bias voltage applied. A low noise and sensitive current amplifier is used to measure the current during the scan. For this form of measurement, a lock-in can also be used to improve the sensitivity. And lastly is current voltage curve, which is IV curve, can be obtained in a DC mode. Next we move to the methodology. In this methodology, the test sample that we use is zinc oxide nanorods. In dye-sensitized solar cell, zinc oxide nanowire arrays has been used when compared to a standard nanoparticle porous film electrode. Electron transport in a nanowire array electrode has been shown to be more efficient. In this study, conductive atomic force microscope has been used to characterize the electrical properties of zinc oxide nanorods. In this study, conductive atomic force microscope has been used to characterize the electrical properties of zinc oxide nanorods. This method has the ability to analyze as-grown nanostructure as well as provide exposure to electrical properties at the nanoscale. This method has the ability to analyze as-grown nanostructure. This method has the ability to analyze as-grown nanostructure as well as provide exposure to electrical properties at the nanoscale. The IV characterization of zinc oxide nanorod with CAFM demonstrates easily rectifying behavior, which may be described in terms of the development of Schottky barrier between the CAFM tip and the nanorods. Objective of this study, where CAFM were applied to study electrical properties of as-grown zinc oxide nanorods to record 2D current maps simultaneously with topography. These measurements have been complemented by local IV characterization of the top and the side plane of individual nanorods. The IV curve were analyzed using the Shockley diode equation. For the sample preparation, the zinc oxide nanorods were grown by thermal evaporation of zinc in dry argon flow on fluorine-doped tin oxide substrate. The reaction was performed in a horizontal tube furnace with a base pressure. The pressure during goods was 1.1 torr. The reaction time was 70 minutes. For the local electrical characterization, first next to the local electrical characterization. The local electrical properties of the nanorods have been investigated in contact mode of AFM. The stability of the feedback loop and the imaging process in general is shown to be substantially influenced by the cantilever force and the scan rate. The conductive probe were coating using DCP-11 diamond from NTMDT. The surface roughness was covered with zinc oxide nanorod is very high. Several requirements should be fulfilled to make the measurement possible. The condition could be achieved on the nanorods with an average diameter of 600 nanometer or larger than SEM. The scan velocity during CAFM mapping was 0.5 micrometer per second or lower to avoid from damaging the tip coating and to minimize the influence of parasitic capacitance effects at the tip to sample interface. The current voltage characteristic were recorded between negative 10 voltage to positive 10 voltage applied to the sample at 0.1 Hz of voltage ramping rate and activated feedback loop. The tip positioning for IV analysis were carried out with scanner in closed loop mode.
That's all from me. I will pass this slide to my group members, Nurul, Damia, to continue this presentation. Thank you.
Thank you, Zara. Hi and a very good day to everyone. My name is Nurul Damia bin Jiraswadi from 4SSCF. So I will be continuing presenting on the CAFM. Firstly, I will be presenting on the interpretation of results and data, which consists of 4 things, which is structural peculiarities, 2D current maps, current line profiles, and IV characteristics. Next is first one. Figure 1 summarizes the structural properties of the zinc oxide nanorods array. So the sample's morphology is presented in the intermittent contact mode AFM image. We observe nanorods with hexagonal cross-section and diameters in the range from 150 to 1200 nanometers. So the crystallographic orientation of the vertically aligned planes is difficult to define solely from the AFM measurements. However, the tilted side planes are sometimes composed of step bunches separated by facets that can easily be distinguished from the rest. So the height of the steps on the side plane ranges from 22 to 30 nanometers. The protruding part of the facet at the steps of the side planes has a width of about 1 to 2 nanometers. So the difference in the electrical properties between the top and the side planes of the zinc oxide nanorods was one of the key issues examined in the present investigation. In order to have an easier access to both the top and side planes, we dealt proficiently with nanorods where the side plane is represented by a number of step bunches instead of one crystallographic facet. So in figure 1b, the section of zinc oxide is shown as a function of the reciprocal lattice vector. The peak positions of bulk zinc oxide with hexagonal lattice constants are marked by dashed lines, and the theoretical peak intensities by crosses. So these positions show excellent correspondence to the measured ones, proving unstrained crystalline zinc oxide nanorods. And then for the 2D current maps, the result of the CAFM measurements are presented in figure 2. Topography images are given in 2D, which is figure 2A, and also in 3D in figure 2B, respectively, in order to provide a better insight into the structural peculiarities of the investigated system. The current maps were recorded in forward and backward scan directions at sample bias of 0.1 volt. So the small values of the applied bias is conditioned by the fact that zinc oxide nanorods exhibit a high conductivity, most likely due to their high surface conductivity. The appearance of the current burst, however, is an interesting phenomenon. The current map recorded in the forward scan direction has been post-processed, and the line profiles taken from the post-processed image are subject of further analysis. The first derivative of the current map is shown in figure 3a. This representation helps to locate the current extrema and has been applied in order to perform a simple analysis of the current behavior at the step edges of the side plane of the zinc oxide nanorods. The 2D current map derivative presented in figure 3a reveals a number of clear bursts coming from the step-like side planes of the zinc oxide nanorods. So next is for the current line profiles. It is a comparison of the profiles taken from the previous figure. Maps with the corresponding topography profile taken from figure 2a is presented in figure 3b. It provides a clear view into the behavior of the current at the step-like side plane for one of the zinc oxide nanorods. Next, for the IV characteristics, the IV characterization on individual upright standing zinc oxide nanorods has been the subject of our study in order to determine their carrier transport properties. It has been found that for platinum iridium coated probes, the IV characteristics are non-reproducible when measuring the tip loading forces. Therefore, the IV characterization of the zinc oxide nanorods has been performed entirely using diamond-coated conductive probes. Then, in fact, the effective electrical contact area has been estimated as 10 nanometer per second by a method, and the current densities J used for the presentation in figure 4b were calculated with this value. The The backward diode current demonstrated in some cases rather significant deviation from zero level at the sample bias higher than 5.5 volt. We also examined the same structure with diamond-coated conductive probes and found the same type of electrical behavior. However, the electrical contact stability was lower at comparable tip loading forces. Next, as mentioned above, CAFM measurements rely on the fulfillment of several requirements such as proper tip loading force, scanning rate, applied bias, and many more. The 2D current maps measured in contact mode CAFM revealed a number of current bursts originating from the side planes of the zinc oxide nanorods. Several possible mechanisms can be responsible for the appearance of the current bursts. The current bursts appear already at very low sample bias, indicating high conductivity of zinc oxide nanorods and low barrier height between the platinum iridium coated tip and the zinc oxide nanorods. Zinc oxide is a wide bandgap semiconductor and the intrinsic bulk conductivity is very low, even if one takes into account that zinc oxide exhibits n-type conductivity in absence of intentional doping. Next, for conclusion, in this work we investigated the electrical properties of as-grown zinc oxide nanorods by means of CAFM. The 2D current maps have been recorded solely in contact mode using platinum iridium coated probes. The current maps revealed current bursts at the side planes of the nanorods and a discrepancy between the scans recorded in backward and forward directions. We assign this discrepancy to be most probably due to the asymmetrical tip geometry, whereas the observed current bursts originate from the difference in the electrical properties between the side and the top planes of the zinc oxide nanorods. So in order to gain more clarity about the correlation between the structural peculiarities and electrical properties, we perform preliminary CAFM experiments on lying zinc oxide nanorods, which are presented in figure 5. So this is the figure for the topography of zinc oxide nanorods. So for IV characterization of upright standing nanorods, we use diamond-coated conductive probes. These measurements revealed Schottky barrier heights equal to 0.5 eV and 0.48 eV from the top and side planes respectively. Thus, the lower Schottky barrier height for the contact to the top side plane of the zinc oxide nanorods also contributes to higher currents. Therefore, this difference of the Schottky barrier heights for the side and top planes of the zinc oxide nanorods should be taken into account when analyzing the appearance of 2D current bursts. Next is the application of the CAFM, which is we have two applications. The first one is CAFM is applied in the nanoelectronics field, solar cell and semiconductor industries for a wide variety of high resolution measurements, including semiconductor dopant profiling and quality control for dielectric films and oxide layers. So secondly, another example of the application of CAFM comes from the catalyst material industry. Fuel cells with cathode catalyst layers consist of platinum nanoparticles embedded in a carbon matrix. The electron transport is dominated by electron tunneling between neighboring platinum particles so that the platinum particle density governs the conducting or insulating nature of the cathode layer. So that is all from me for this presentation. Thank you.